Good afternoon, everyone. Thank you very much for coming here. And today we are very honored to have Professor Larry BIEGLER presenting for us as an IAS distinguished lecturer. So let me give you a little bit of introduction about Professor BIEGLER. So, to many of you, this might not be necessary, but yeah, to the others, right? So he's one of the most prominent person in the area of process systems engineering, right, which is a pillar area for chemical engineering. The most difficult things you learn, right, optimization, control, right, those are the contents of process systems engineering. So Professor BIEGLER is the Covestro University Professor of Chemical Engineering at Carnegie Mellon University. His research interest lies in computer-aided process engineering. That includes flow sheet optimization, optimization of systems of differential and algebraic equations, reactor network synthesis, nonlinear process control, real-time optimization. So his contributions include development and analysis of nonlinear programming algorithms and application to real-world chemical and energy processes. He's an author of over 600 publications and 2 textbooks, and he has edited 11 technical books. He's a fellow of the AICHE, IFAC, and SIAM, and a member of the US National Academy of Engineering. So today he's going to talk to us about the concept of digital twins and its application in process optimization. So without further ado, I'll pass the time to Professor BIEGLER.
Okay, thank you very much, Professor Gao, for that kind introduction and especially for the invitation to visit HKUST. It's really good to see some old friends again here at HKUST and also to make new friends. I've fondly followed the progress of this great university over the last 35 years, starting with colleagues from Carnegie Mellon that actually visited here and actually spent some time here, even took positions here. So it's been a real pleasure to come back here and to learn more about the place in real life, in person. So what I wanted to do today is I wanted to share with you some of our experiences in looking at digital twins and AI and how they relate to process engineering, especially optimization, okay? And so there's a question mark in my title. And what I'd like to do is, before I get started, give you a little bit of background of what we're talking about here. So what I really wanted to mention is, first of all, where I'm from. Okay, this is Pittsburgh, Carnegie Mellon University. And at Carnegie Mellon University, CMU, we have something called the Center for Advanced Process Decision Making. Okay, what we're doing here is basically we have a collection of my colleagues here that have been around for a while, and others are quite new. And what they're doing, for example, Professor Grossman, he's the senior member of the group, has been there for a long time. And what he and I did was put out this book, okay, with Art Westerberg, which is, well, it's been around for a few years, but still useful in some ways. And then I have my other colleagues here. Carl Laird is now department head. David Miller is the co-director of the center, along with me. And then Chrysantos Kounaras, Anna Torres are also PIs on these programs. And we also have some adjunct professors as well. So what I'd like to do is mention that this topic is driven by real-world problems. So, in fact, we have worked on algorithms for what we do. We have currently 6 faculty, as I showed you here. We have some interesting research topics as well. And currently we have 30 PhD students in our program. And probably more importantly, in the past, 33 of our PhD students are now in academia, continuing this research at other places. Okay, so having said that, we also have some industrial interactions. And here we have about 20 companies that we work with, and they help us guide industrial projects. They're using some of our tools, and they're proposing new problems for us to work on that actually guide our research and help us in terms of thinking more about contributing to the field as well as solving real-world problems. So that's basically just a little bit of background. What I'd like to do is give you a little bit of a roadmap where I wanted to go here, talk about digital twins. Okay, one of the things that I feel very strongly about, and I see it here as well as in a lot of other places, is to use optimization strategies as an engineering tool, okay, for decision making. And I'll give you a flavor of that, how that actually works. What I'd like to think about is we all make models, mathematical models. We all use those models to get some idea of how to make a decision, either through modeling or simulation or a calculation. I'd like to take that a step further. Let's not simulate to make a decision. Let's optimize to make a decision. Have that optimization problem take care of the best parameters, the best set of conditions for you to make that decision, so that you don't waste time trying to find those yourself, okay? So that's one of the things we're doing. I'm going to show you the motivation for this idea here with reduced modeling is why people are talking about digital twins. It's the idea of saying that we have systems that are very complicated. They may or may not be described by truth models, but more than that, they need some reduction. And I'll give you some examples, talk about a way that we would like to do optimization within the framework of those models. And then I'm going to talk a little bit more about this idea of PINs, physics-inspired neural networks, and go to something that I coined myself the other day, which is PENS, physics-enforced neural networks. And there is a difference. Okay, and then conclude. Okay, so to get started, what are we doing here? We're starting off and saying, why do we do optimization, and why do we do something called nonlinear programming for optimization? So this is a different NLP than what usually people think about in AI. But nonlinear programming is basically the idea of having nonlinear, continuous variable optimization strategies. You usually have some kind of a process model over here, and you're taking optimization algorithms, setting certain conditions or some certain profiles, and then running this kind of repetitive algorithm in order to converge to the best point. Well, this is one way to do it. In a way, it can range from anything from case studies to more sophisticated algorithms, but what you're doing here is you're always repeating the same model over and over again. And this can be not only expensive, but sometimes it doesn't work. We have another strategy, which is basically to say, let's not search, let's solve for the solution. And that's where we essentially formulate the problem and the solution strategy so that it all pretty much gets together in one go, all right? And so what we're doing over here is rather than repeating this model over and over again, we're actually solving both of these at the same time. And when we can do that, we come up not only with a faster strategy, but something that is often more reliable, more efficient, and more robust. And that's basically something we're going to talk about today. All right, that's the idea. And this is not really that new. If you go back 4 decades, back maybe when I started my PhD thesis, these are the algorithms that have evolved along with that strategy. Okay, if you look at some of these names here, what you see is SQP, successive quadratic programming. This is something you will find in every process simulator, from Aspen to Pro2 to HKUST. And this is something that is a standard tool that you'll find, and it solves problems reasonably well with 100 decision variables. Okay. Over here, there has been a framework that extended SQP to reduce space SQP. And this thing here now solves problems that are real-time optimization problems with over 100,000 variables and constraints. And if you look at a chemical plant or a refinery that is running RTO, These problems are solved every hour. They can basically adjust to changes in ambient temperatures. They can adjust to changes in product prices or raw material prices. And they can adjust also to the quality of products or raw materials. And you can update your optimization every hour by solving these codes. Well, in this century, we came up with another algorithm called IPOpt, which I think can solve, under the right kinds of problems, we can solve over now 1 million variables and constraints. So this is something that's nice because we don't have to limit ourselves to small problems. We can actually solve fairly large problems. And what's nice about it is the way we solve this simultaneously, you get sensitivity information that you can use to update your solutions in very little time and with very little effort. And that's basically the last thing here with SIPOpt. So I wanted to just make mention of this because we do have large-scale optimization strategies. We'd like to use them to the best benefit we can. Okay. Now, here's the challenge. The challenge is take something like this. Okay. So here's a fairly complicated flow sheet. This is for the integrated gasification and combined cycle. This is a flow sheet that was proposed to take care of carbon capture. Okay, so what we're doing here is we're starting off with coal and water. That was still a very popular thing in Pittsburgh and in parts close to Pittsburgh. We'd like to develop clean coal, which means that we will be able to take all of the nasty parts of coal, separate them out, and especially take care of the nasty part called CO2, and take that out and basically sequester that. All right, so this was a popular process. And what's important here is all of these parts not only give you a large problem, but they give you a problem that resists writing it down as a set of equations. Instead, each of these is a separate plant, okay? And that separate plant over here requires specialized solution procedures that take a long time to solve. And then you'll probably ask, well, wow, I mean, I can solve these things simultaneously, but if it means that I have to open up each of these red boxes and reconstruct a new algorithm, that is going to be extremely expensive and actually not worth the effort. So then the question is, how do you solve a problem like this? Okay, let's go and take a look. Well, I think you know the answer. We come up with a digital twin, okay? Some kind of a reduced model or surrogate model that basically takes each of these red boxes over here and turns it in with enough data or simulation that allows you to put it back and formulates an optimization problem that is easier to solve, okay? We could do that. All right, so if we do that, then what we'll do is say we got two methods to go about doing this. One is to say, let's do model reduction based on a physics-based approach. So you look at the models inside each of these. You have conservation laws, mass, energy, momentum. You have performance equations, things that tell you how to describe the behavior of each of those red boxes and more. You have constitutive equations that depend on the composition, depend on the conditions under which you're running. And then you have physical component properties. So each of these has a whole class of equations that you have to put together. Now, let's ask the question. Suppose each of these is rather tough to solve, challenging to solve. What do we do if we want to do a physics-based reduction? Well, we think about the assumptions that we used for these strategies. And these assumptions that we use, let's see if I can get this to work. Yeah, oh, sorry, let's go back. Okay, these assumptions here allow us to come up with physics-based shortcut models, right? So you take the partial differential equations, you can use PCA or POD to make these smaller PDEs. You can take models with molecular weight distributions or particle size distributions, use moment models. You can take into equilibrium stage models or even mass transfer models, make them into equilibrium stages, then turn them into shortcut methods. And similarly with physical properties, you can make some simple regression problems, okay? Why do we do that physics-based approach? Well, it's mainly because you can decide what assumptions you can make that can hold when you go from something, very rigorous to something simpler. And when you get the solution of that something simpler, you can see if those assumptions are validated. And that means you have an interpretive or interpretable result, okay? And interpretation is a clear part, a very important part of what it means to get an optimum solution, okay? You know under which conditions it's going to be true. All right. Now let's take another approach. This requires us to know the physics. This one here requires us to think a little bit more about data, okay? So instead of knowing the physics, why don't we just run these simulations in background somewhere overnight or over the weekend, and then say, okay, I'm going to generate a bunch of data from those red boxes, and I'm going to use that to build data-driven models. Those data-driven models are based on experimental design, basically finding out what's going to happen with, with which data points or simulation points do I run at, and there's a variety of these that I can use. They get expensive if I have a high dimension, but usually they work pretty well, and this is a popular one over here. The next thing is, how do I represent my model with those data points? Okay, what kind of model do I put together? You can see some very popular ones: polynomial, radial basis functions, Gaussian processes and Kriging, neural nets. Those are things that you'll find as very common, especially now with machine learning. All right, and the last thing is, of course, how do I train the data or the models based on the data? Okay, and so over here there are many ways to do this, especially with machine learning. There's some very popular large-scale algorithms that are used a lot. Okay, so based on that, how do I build these models? Well, first of all, there are challenges because we want to make sure we have an accurate fit, we have well-conditioned models, well-poised models. We want to make sure that you get the same output when you run these models several times, not over-parameterize them. And then the question is, how do we have an interpretable model? Okay, and to give you a flavor of that, I'd like to show you a little bit more about how we want to do optimization with these models. So let's take a look at a case study. So let's move forward and think about this problem here. We're solving this optimization problem here. So think back to that flow sheet with the red boxes. What we have over here is this problem over here, okay, where we have variables that are basically from the overall process, mostly mass balance equations. We have an input to one of those red boxes, and this TW is the output of those red boxes, and we call that the truth model, the simulation model that it's going to be expensive to solve. All right, what we're going to do is we're going to lift that truth model, add this variable y over here, and move that over here, write another equation. Simple idea. We do that because we want to isolate the truth models, okay, and that's what we have over here. And then we do what everyone wants to do, is to say, okay, get rid of the truth models, because what I want to do is I want to solve this problem faster. The other parts of the problem I can leave over here. The truth model I don't want to run, and so I'm going to come up with something that I call a digital twin. So that model here gets replaced by a reduced model, okay, which comes from the previous two slides, okay? So it basically looks like that. All right, now, what good does that do? Well, it's what I call one-shot optimization. Now you basically run this model and you use the results for what you want to make a decision on. Okay, very good. Here's an example. Okay, this is one of those real-world problems that's going to be interesting to solve. We have some steel mills, okay? We have a steel mill with point sources of CO2, high concentration CO2. And what we want to do is we want to clean them up. So we have a standard technology here that's called basically, this is going to be carbon capture using an adsorption-based process, okay? So we have an absorber here with a certain amine scrubber, which is basically something like MEA that we're going to use, methanol ethanolamine. And we're going to have a stripping column, okay, that regenerates the CO2 captured here by the rich amine, and then basically separates the CO2 from everything else. And what's the lean is amine that's left goes back into the absorber and runs it again. Okay. Now this may be fairly straightforward. You look at that and say, okay, standard process, let's use it. Realize that both of these columns are not just simple separation columns. They're PDEs that involve nonlinear physical property equations, electrolytic solutions, and reactions, and then also basically a very interesting transport problem over here. So that's basically the problem that we need to solve, okay? And if we do this, we're going to find out that we need to take all of these point sources, we consider this flow sheet or a bunch of these flow sheets that we need to design, and of course we want to separate out the CO2 at minimum cost. All right, so let's take a look at that. Okay, so that's the problem. There's the steel furnace, okay, and we've got 8 streams here that are high concentration CO2 that we want to basically take care of. And what we're going to do is we're going to say, okay, great, with these 8 streams, what I want to do is I'm going to take those and send them to some of these plants to do carbon capture. Which ones do I send? Okay, and where do I put them? All right, so here are the 8 streams, okay, and what we see here is basically the amount of CO2, this is in megatons per year, okay, and flow rates are given here, compositions are given here, temperature and pressure and so on. Which streams do we send to which unit, which scrubbing unit, and how much of those do we do? So this is a pooling problem. We pool them together, blend them and pool them, and we want to design the plant that takes care of scrubbing them, all right? That's the plant that takes care of scrubbing them. Basically, this is the one. And if you look at this problem here, it has about 50,000 variables and constraints, okay? So it's not unreasonable, but it's something that's time consuming. And that's only part of the problem because the rest of it is trying to figure out where should the streams, the input stream here comes from where, okay? And that's the pool. So now what we have is basically inlet properties over here. Basically, this is basically the amount of streams that we have, the composition, the number of transfer units in this thing here. And then at the output here, we're going to say I've got the total annualized cost, and I've got the capital cost and the operating cost over here. This big red rectangle is our truth model, okay? And what we want to do is figure out, is that the best way we're going to solve it? So let's take a closer look at this thing. What we're going to do is try to figure out what's the best reduced model that we can use to solve this optimization problem over here, okay? That's the optimization problem. If you look at it, what's in the green box there, okay, this thing here was that plant on the previous slide. The rest of the optimization problem is basically just mass balances from the point sources, specifications on what we need to capture from the point sources over here into what comes out of the scrubbers over here. And of course, what we want to do is minimize the total annualized cost per ton of CO2 capture, okay? So we want to know, yeah, what's the price of CO2 captured that we can get that's the minimum price, all right? Given that we have that, this is the problem we want to solve, okay? Good. Now let's take a closer look at this. What we're going to do is we're going to say, these are all the individual properties that I need and the equations that I need. I want to know, can I replace the truth model with this model over here, which is going to be, which is going to be my digital twin. My truth model gets replaced by a digital twin, okay? What digital twin do I use? Okay, and what's in purple, those are going to be my outputs of the digital twin. What's in green are my inputs of the digital twin, okay? All right, good. Let's take a look. Well, the first thing we can do is say that's basically part of my one-shot optimization where I replace the truth model with this digital twin model over here, okay? Oh, yeah. Okay. All right, so let's take a look. What I'm going to do is I'm using this framework here, by the way. It's a very nice framework that we're using based on Python. And this is using the Aspen model over here. We're using a Jupyter notebook to access a very powerful set of optimization tools in Pyomo over here. We can add surrogate models from a certain library here, and all of that can be put together and integrated into one solution strategy that combines the optimization algorithms. We're solving this with IPOpt in IAS. Okay, and so the question is, which digital twin models are the best ones to use? All right, let's take a look. So what I have here is I've got my digital twin model, and I'm going to start with polynomials. Very simple model here. This is implemented in a package called Pismo, Python surrogate model optimizer. And so what this does is simply take these inputs, quadratic polynomials, and has these characteristics, okay? Not too bad, but what we find out is it's not terribly accurate, okay? So you're seeing training data over here as the problem size gets bigger. The validation data gives much larger errors, you can see over here. And eventually it settles down, but not at a great level of accuracy. And this is the CPU time, which is actually quite fast, okay? So that's one way to do it, but it's not the best way. Let's take a look at the next one, which is using something called Alamo. Alamo is a tool that is based on linear regression, but it also spends a lot of time trying to find the best basis functions in order to fit the data, okay? So there's some combinatorial decision making done over here, find all these coefficients with linear regression. And what this is doing is using a Bayesian information criterion to basically decide among those basis functions that work the best and minimize the amount of terms here. All right, when it does that, it solves a mixed integer linear program, and you can see, okay, the training data, that goes down over here, that goes, basically stabilizes over here, the test data, or validation data, that one basically stabilizes as well, much better than the polynomials. CPU time, well, it's not too bad, but it certainly goes up with problem size or data size. Okay, this is so far the fastest approach and does really well in terms of accuracy. Okay, let's keep going. Well, here's one that uses, this is one that uses radial basis functions, okay? So that one there is basically much more nonlinear, and we can see that this is going to take more time. It's reasonably accurate. You can see the training data in blue, that's working pretty well. The test data or validation data, that's reasonably accurate. But take a look at the right axis. This is much more expensive. This is now an order of magnitude more expensive than what we had before, okay? So you pay for this in terms of the amount of training you have to do. Okay, next one, Gaussian processes, kriging, okay? And so in this case, you're doing a lot of work to generate these models. The nice thing about Gaussian processes is that they not only fit the data, but they also tell you how much error you can expect from an inference, okay, on that data. So that's a very valuable thing. And you can see similarly, the blue and the green lines tell you that the training and the validation are doing pretty well. The right axis now is an order of magnitude more than what we had with the radial basis function. So this is expensive, okay? All right, next one, neural nets, okay? Neural nets, you have that form over there. In this case, we took 2 hidden layers, 18 nodes per layer. And you can see over here, this is even more expensive than what we had with Gaussian processes, okay? About twice as much. Not too bad in terms of the accuracy of the data, fitting the data, but you know, that's what you end up with. So you end up with a high training burden, but a fairly good, fairly good accuracy on this. Okay, so five different digital twins. We put that in the optimization problem, and we run it. There's the result, okay? So the optimization problem isn't too hard, okay? So once you have the reduced model, this thing runs, you know, anywhere from 42 seconds to maybe, 4 minutes, okay? Depending on which digital twin you use, so that's pretty reasonable. The objective function is also very different, okay? And the first question you want to ask is, all right, you've got now 5 different results based on 5 different digital twins. What's the right answer? Which plant do you actually build, okay? Well, you can look and say polynomials, that's a nice objective function, $37 per ton of CO2 recovered. But there are some other issues. First of all, take a look at the solution, okay? And you can see that each of these has a different blend, okay? So this point source here, well, that one says, well, you can use some of it, but not all of it in some of these results. The rest of them say, go ahead. This point source says, well, some of this I'm not going to take at all, and then this one gives you a different blend as well. So which one's correct? Well, the question we have to ask is, there's a 7% difference in the objective. More importantly, which of these is even faithful to the truth model, okay? And in fact, that's part of the problem. Some of these digital twins, they actually fit the data pretty well, but now they move to a new point, and who knows how well they work at the new point, okay? In fact, there are lots of cases where they pretty much don't predict what the truth model will tell you. Just to not to belabor this point, this is something we discovered in a different case study, where we had a digital twin that was used on steam table data. So you have this table of thermodynamic properties of steam tables, and you want to basically build a digital twin that models your properties, the enthalpy of steam tables. Okay, from thermodynamics, you know that the dependence of the enthalpy on pressure, well, as the pressure goes up, the enthalpy goes up, but only by a slight amount, okay? If you have an ideal gas, then the enthalpy, of course, is not affected by pressure at all. But if you have something like water, then yes, it's going to be affected a slight amount. Build this digital twin based on the data that you have from the steam table, and it doesn't fit this model perfectly. In fact, it looks like this. And what happens is it's not just the value that matters here, it's the sign, the slope of this equation. Because it says, is the trend as pressure increases for enthalpy to increase or decrease? Okay? Well, if it increases, then it means that it says as you compress to high pressure, then this is going to cost you more money because you have to heat it up more. Okay? If the slope is negative here, it says run your process at a high pressure and build more compressors, because actually you're going to be making money by running high pressure steam. And you'll probably win a Nobel Prize, but it's absolutely wrong. And that's what we found out when we made a digital twin based on regressing this steam table, okay? And it told us, yeah, that your surrogate, your digital twin, should give us compressors that actually create work because of the slope of this curve, okay? So, not so good. Real question is, how do you validate that you have converged to the optimum of the truth model? That's what we want to know, okay? And here I want to show you how we do that. Okay, so we have this thing here. We had these 5 solutions, okay? And now what I'm going to do is I'm going to say, how do we test those 5 solutions? Well, at a certain point over here, I'm looking for the optimum over here, and I've done my training at this point here, and the optimizer says, move over here. Is that a good point or not? We're going to check it. In fact, what we're going to do is we're going to start out by putting in what's called a trust region and finding out how much does it actually change inside the trust region. And we adjust the trust region to make sure that this doesn't contribute a lot of error due to the digital twin. So we actually monitor the difference between the digital twin and the truth model. Okay, based on that, we may not want to take that direction. In fact, what we'll do is we'll go to something like this, okay? And then at that point, we move the trust region, and what we're going to do is say, okay, at that point, we solve the problem again. At that point, what we're going to do is we're going to say, okay, with that problem, we're going to move forward, but only inside the trust region, So what does that mean? We all formulate the problem this way. We take what we had with the one-shot optimization, which was this problem over here, and we had this trust region here, okay? That trust region here prevents how far we can move from the current point, which is xk, all right? Now, what we're gonna do is we're gonna say, I'm gonna adjust that trust region based on how well the truth model at the new point fits the prediction by the digital twin, okay? This is theta. If theta is going down, I know I'm making progress, and that's a good thing. If it's going up, I have to shrink the trust region, okay? That's the idea, all right? So we keep doing this until we converge, okay? All right, we manage the trust region by doing something like this. We have a filter. The filter is actually where we're at a point like this, and we check whether the objective function is going down or theta is going down, or both, okay? So take a look. Here we start off and say, great, the objective function is going down. Theta can go up or down. And this is called an F-type step. So then we can increase the trust region. We may be at another point here where the objective function is going up, not so good. But theta is going down, so that's good, it's getting more accurate. It's called a theta-type step, okay? And in this case, we're not gonna adjust the trust region, or we might a little bit, but what we are gonna do is we're gonna take a look and make sure that this point here gets added, and we only work inside this region over here. Otherwise, we don't make any progress in the optimizer. That's how we basically force it to converge. All right, so this is the filter method. When we put that together, what we end up with is this the algorithm here. It's fairly simple because what we're doing is we're solving a problem over here that is the same as the one-shot optimization with my digital twin. And then what it's doing is checking that digital twin over here with the truth model. That's the difference. Based on that, we do our trust region management over in these boxes. So that's a fairly straightforward algorithm. Now, if we are lucky enough to extract derivative information from our truth model, it gets even easier, okay? And that's basically our algorithm. So let's see what difference it makes, okay? So I'm gonna run this algorithm on my 5 digital twins, and what I end up with is, well, these are the properties of the method. If you're interested, there are actually convergence proofs that show how this converges, either without derivatives or with derivatives, okay? And so you can actually prove that under these conditions here, you can actually come up with very fast algorithms that converge for any digital twin, okay? Under certain, well, mild conditions. But this works for any digital twin, okay? You pick your poison, this will actually converge, okay? Okay, so that's the result that we have from our analysis. Okay, good. So, Alamo, take a look at that. What I'm showing you here are the orange bars. That basically tells you what the error is in your fit between the digital twin and the truth model, okay? The green bar is the size of the trust region, okay? And it's nice if it can shrink, but if it remains large, you converge faster. And the black dot here is the objective function. So you'd start up fairly high over here, it cuts back, and then basically sends you to something lower, and this is the objective function over here. And then finally, it converges to something over here. All right, so that's how it converges. After 4 cycles, you basically go from something where you had a high error to something that is 2 orders of magnitude lower over here. That's Alamo, okay, after 5 cycles, okay, of this algorithm that I showed you. All right, run polynomials. It has more trouble, but it converges after 9 cycles. And again, the objective function, this guy here, is about the same as what this is, okay? Run the radial basis functions. This takes 7 cycles. And again, the objective function is about the same as what you have with the 2 others, okay? And again, what you're seeing here is that this infeasibility is going down by 2 orders of magnitude. All right, now, take a look at something else. This is what we're doing. We're seeing a difference with this objective function going up and the infeasibility going down in each of these cases. And you're ending up with these 3 points here that are about the same. Now, take a look at the others. Here's your GP, your Krieging, okay? And again, at this point here, you have an infeasibility that basically is reduced by 3 orders of magnitude when you go from here to here, one cycle with the trust region algorithm, okay? And again, objective function very close to what we have to the others. And with neural nets, what you're seeing is a very similar experience. In one cycle, it takes you from something that was not very close to the truth model, and it goes down 3 orders of magnitude, and again, pretty much ends up at the same point. Okay, so what you're seeing here is a difference between solving the problem where the infeasibility with the truth model goes by at least 2 orders of magnitude down, and what's happening is your difference in the objective function, that's dollars per ton of CO2 captured, goes down from 7% to just 1% difference. If you wanted to tighten the tolerance and run more cycles, you can get it down even more. But the whole idea is now you can guarantee convergence to the truth model without having to solve the optimization problem for the truth model. And you can solve this with any digital twin you want. Just to emphasize that, I'm going to show you kind of a catastrophic case next. So these are the takeaways. They give you the relative advantages of each of these digital twins. Polynomials, not so good. Alamo actually was the fastest training time and good accuracy for the result. Neural nets was very accurate, and one cycle took you to the truth model with the trust region, but this had the highest computational burden by far. You need a lot of data. Compared to this one, we're talking a difference of 3 orders of magnitude in time, okay? And Krieging, not that much different from the neural networks, maybe a little less data. Okay, now I want to emphasize how good does your digital twin have to be to converge, okay? So in this case, we took a little bit more and we talked about, well, let's do a physics-based digital twin, okay? So again, we have our truth model over here. Oops, sorry. We have our truth model over here. We have our digital twin over here. Sorry. Yeah, we have our digital twin over here. Then what we do is we say, okay, let's take a look at this flow sheet. We find out that this was a problem that had about 50,000 variables and constraints in it, about 45,000. And the truth model here, for that, just that absorber alone, remember it's a discretized PDE, very nonlinear. That one here, that absorber had 90% of the equations and variables compared to the whole flow sheet, okay? So what do? You say, well, clearly I don't need a digital twin of the whole thing. I can just basically take this model here and create a digital twin, and I'll use a shortcut model for the absorber. Easy. Okay, so let's do that. What do I choose for my shortcut model? Well, suppose I choose a digital twin over here that is no shortcut model, 0. And every time I go through a cycle, I'm going to add the bias from the digital twin and the bias in the derivative of the digital twin. That's all, okay? And that's how I update my shortcut model, okay? Okay, I could do Alamo, okay? So this one here, this is going to take 13 hours of training time in order to come up with this model, because I have now more degrees of freedom, and it took overnight to get this, all right? And then what I could do is I can look up in Aspen and say, well, what does Aspen do? And Aspen has a shortcut model based on certain assumptions that, well, assume equilibrium stages, assume some correlations, and I can put that in. It's physics-based, but who knows how accurate it is. So I put that together, and what do I get? Well, in this case, what I get is something that is the shortcut model is now 4,000 equations instead of 46,000 equations, all right? You can solve that, all right? If I have a 0 digital twin, okay, nothing except my bias updates, this thing is going to take about 20 iterations, 21 iterations, okay, cycles. The infeasibility here is given by the gray bars, okay, and what I'm seeing, and what I'm seeing over here, actually, no, the trust region is in the gray bars. The blue bars are the infeasibility, and you're going from here down to something that is orders of magnitude less, okay, basically 8 orders of magnitude less in infeasibility, and the objective function basically dithers around and finally ends up at this point. All right, now take a look at Alamo. Alamo is going to have this result here, where it's going to take only 5 cycles, okay? Or sorry, 7 cycles. It's going to go from this infeasibility to something that is much, much less, okay? The objective function turns out to be exactly the same as what I get if my digital twin is 0, okay? And now if I go with this model over here, which is basically something that gives me, well, it gives, if I take this and I use this shortcut model over here, that shortcut model is going to be something that doesn't cost me any training time. Again, I get some really radical decrease in my infeasibility from here to here, and the objective function is exactly the same. And now what I'm going to see is after 5 cycles, this guy here basically takes me to the truth model optimal. Okay? The original model, when you solve it with 46,000 equations, is this one. This one you have to solve 5 times, okay? And each time this is going to take you 26 seconds, and then you end up saving overall more time. All right, so this is basically the idea. So if you want the truth model optimum, you can do it this way. And what you can guarantee is that that will actually work with almost any digital twin you can think of. Good. So that's basically the answer to working with digital twins and basically getting to the truth model optimum. So these are some case studies that we got. We've applied this to polymer processes going back 10 years. We've looked at power plants, and we're doing CFD models with this approach here. We were looking at refinery optimization, basically where we had surrogate models for an FCC unit, heat exchanger networks with MINLPs over here. And more recently, we've been looking at a lot of different kinds of units, including pressure swing adsorption, amine-based absorption. Well, I showed you a little bit of that, even direct air capture, okay? And so those were things that we were able to do with digital twins, and all sorts of truth models that ranged from CFD to Aspen flow sheets to other PDE models. Okay, so in the time that we have left, I wanted to talk about another use of doing large-scale optimization tools, but not so much for guaranteeing the truth model optimum with a digital twin. It goes back and asks the question, how do I get a digital twin? How do I train this from data even if I don't have a truth model? Okay, that's a common question. It's great if you have a very detailed truth model. We know how to handle that. But what if you don't have that? Can I still do better on my optimization? So basically, these are the conclusions that we have over here. Before I get into that, just tell you that if you do one-shot optimization, optimizers will cheat, okay? Sometimes they will find the hole that you didn't get with your data set and with your training, and it will go through that hole and give you a model that has a large truth model mismatch. It can happen. Here are some truth models that some digital twins that we used, okay? And what we can guarantee is satisfy the optimality conditions for the truth models using a variety of digital twins. Almost no requirements required. Okay, good. Let's go on. What we want to do next is we want to talk about how do you do the training in this case. And if you think about how machine learning has evolved, you're basically saying collect some data, okay, hopefully not too much, and with that data, you're going to get a cheap digital twin or reduced model that looks like this. And if this is the real model, the ground truth is from here, well, you've got some errors, okay? And fortunately, if you use something like Gaussian processes, you'll be able to get some kind of a characterization of how bad the error could be around each data point. It's not perfect, but it gives you some idea of how well you're fitting the model. That's good. Okay, based on that, how can we get better than that? Well, what we're doing in this case is we're going to say, great, there's the evolution of the truth model, but what I know is that there's some physics involved. I don't know the entire truth model, but what I do know is that I have some physics here, first principles, and then over here I have some data that I can fit with a neural net, machine learning, okay? And now what I'm going to do is I'm going to say, great, suppose I have something in between, okay? So in this case, what I'm going to do is say, if I have a pure ML and I know some physics, then what I can do is basically have something in between. Instead of going from minimal data to extensive data, or going from a pure ML to first principles, I'm going to go for something that has some physics and requires a moderate data set, okay? That's what I'm going to do. This is nothing new. People have been doing this since the 80s, and what they've been doing is saying, okay, I want guaranteed constraints and I want enhanced interpretability based on some physics-based model, okay? So what you do here, and here's a little example about dynamics that has physics incorporated here, is you can get an ML based on data from here. Or what you can do is you can say, let's go ahead and find out, let's see now, yeah. Let's go ahead and find out what the physics are. And I'm going to try to capture the physics with some approach, okay? And the approach that people like to do is to use PINs, physics-informed neural nets, okay? And what is probably less obvious is it's based on the fact that you know some of the physics, but you also are trying to leverage your training tool. For example, when you use something like Atom or some other variant of stochastic gradient descent, you're going to formulate an optimization problem that looks like this, okay? You have the data loss and you have the physics loss, okay? And then you use this unconstrained algorithm for phi to try to get that to be close to zero, all right? Well, the problem with this thing is you are balancing your data loss and your physics loss with these parameters here, and the only way that you can enforce the physics in your digital twin is by making sure that m goes to zero, all right? Otherwise, you're always going to deviate from the physics, okay? And so this is a problem, because this guy means that if m goes to zero, you're losing this data loss term, okay? You might as well not have any data at all. It's going to focus on this guy alone, okay? So this is a problem with physics, with pins, and so what people do is they say, well, okay, m isn't going to go to zero, but we'll basically fudge it and try to get something that's better than what we had before, all right? And what we need to do is say, physics needs to be enforced, especially if I have constraints that need to be satisfied based on the physics, okay? So let's see what happens. Okay, we've got lots of different safety constraints, path constraints. I think the difference between generative AI, where you can ask questions and get answers, and putting machine learning in a chemical plant is that the chemical plant can explode if you don't satisfy the constraints, okay? That's why it's much nicer to have generative AI on your computer than in the control room in a plant, okay? So we need to actually find out a way to keep physics enforced, okay? This is the way we can do it. What we're going to do is say, formulate the optimization problem, this problem for training over here, add the physics that you know, and add a neural net for what you don't know. And then you solve this optimization problem. So we're going to go from physics-informed neural nets to physics-enforced neural nets, from pins to pens, okay? And we're going to basically say, don't use stochastic gradient descent. There's some real advantages for that, but we have to go beyond that and take advantage of the large-scale optimization tools that we still have, okay? And that's what I wanted to focus on toward the end here. So what are we doing here? Well, it depends a lot on how you formulate this, and we're going to talk about neural DAEs, okay? So we're basically going to have a differential algebraic equation set, and we're going to model part of that with machine learning, okay, with a neural net, okay? What people have done in the past is they used sequential methods, and here are some references, where they take an integrator and solve the DAE, okay, and basically extract some sensitivities and throw that up into, your algorithm that basically does the fitting, okay? That seems to be a straightforward approach to go, but it has three disadvantages. The first disadvantage is that if your DAE is unstable, the integrator may fail, and then you're left with nothing in between. The second disadvantage is that sometimes these DAEs are high index, and you can specify the wrong initial conditions, and the integrator will fail, and you're left with nothing. The third thing is the fact that when you look at solving this problem here, you have no way to satisfy the constraints of operation of your dynamic system. The integrator ignores them, okay? So we went to a simultaneous approach where you discretize the problem. Instead of having a small optimization problem with your integrator, you form a large optimization problem here by discretizing everything in time. So you end up with a system like this. You convert these DAEs, differential algebraic equations, into basically a fully algebraic problem by discretizing everything here, algebraic variables here, differential variables over here, and then what you turn in from a digital twin over here with your neural net, okay? All of that has to be collected into this larger optimization problem. Okay, so let's see what we can do with this problem. If I put it together, then I've got my discretized differential equations over here, and now I'm going to solve that. Okay, let's take a look. This part here, z, I take out the equations that are difficult, and I put in my digital twin, which is my neural net over there. Okay, so I want to train this digital twin on my data, okay? And so what I'm going to do is going to say, okay, we're going to expect that collocation is now a large-scale sparse problem. Okay, that's nice. To solve the NLP, we're going to use an interior point method like IPOpt, okay? And we can solve very large problems with this quickly. And we can refine this with initialization schemes, and we can also refine this with looking at approximations to our second derivatives. Won't dwell on this, but I wanted to show you how well it works. Okay, so here's a bioreactor, and we're going to solve this with pens, all right? And simple equations here, okay? We have biomass, we have our product, we have our substrate, and we have our volume. Control variable is actually the amount of feeding of our volume, okay? And what we're looking at over here is we're saying, I don't know this specific growth rate. That's the part of the physics I don't know. The rest of it is basically mass balances. Okay. The truth model is in here. And I want my digital twin to find my truth model. Okay. So now I build an optimization problem where this is the objective function, and I train on this objective function. This is going to be my digital twin over here, and these are going to be my neural net that I have to fit with these parameters theta. Okay. Now, we did this, and we solved this problem now by taking, we took two trajectories. We had 20 neural nets, and we had 2 layers, okay? Sorry, 30 neurons, 2 layers, 20 finite elements, 2 collocation points, 10,500 time epochs, and this solved with simultaneous collocation, 29 seconds. Okay? If you do it with a sequential approach, it takes more than, well, almost twice as much here. Okay? So this respects the conservation laws, and what's nice about using this, the ground truth is in black, okay? The simultaneous method is in green, and if you squint and look really closely, the simultaneous method and the ground truth method will not violate this lower bound, okay, which it shouldn't based on the physics, okay? So that's one way the simultaneous approach will take care of those things and train your neural network in a nice way. Okay, so that's one thing to do. There is an issue. How well does it scale? And this is where the fun part is. This is the problem we're going to solve. There's the neural net. But now suppose you have a ton of data and you want to use a deep neural net. Lots of layers, lots of neurons, lots of weights in your neural net. How does the optimization problem scale with the best algorithms? Well, the answer is not so good. Why? Because large-scale algorithms like to exploit sparsity in the structure, and this neural network over here, it ain't sparse, okay? And that's going to be a problem as the size grows. So what did we do? We thought, okay, the fully simultaneous method that I showed you in the previous example, that one worked pretty well on a small neural net, but because of dense structure, it can get pretty expensive. And so what we're doing is we're saying, let's reformulate this. Let's use some knowledge about the optimization. And what we're going to do is we're going to say, let's come up with a model. The model is over here. The model is over here, where we take this neural net and this objective function, and we say, why don't I solve only for theta? And I'm going to train theta using an SGD or atom. And I solve that on the outside. And on the inside, I solve an optimization problem with a fixed theta and solve the rest of the problem on the inside. Now, when you do that, what is nice about that is you end up with an outside problem that only is dependent on theta and the variables on the inside, which are also a function of theta. And so that's the upper level. You can use SGD for this. The lower level, what you're doing is you're solving the optimization problem, except without the thetas. Thetas are now fixed. And so this, you can use your standard large-scale optimization problem with a fixed neural net. Okay, so we do this, and we put it together, and using JAX, we can actually extract from the optimality conditions of this problem, we can extract the gradients that we need for the outside problem that are going to be used by the SGD. So if we do that, the question is this any better? Well, it turns out sparsity matters, all right? And so here we have something that's very sparse, and all the dense stuff is handed over to our training tool. Okay, so when we do that, here's an example, the quad tank. What we have over here is this part here is unknown. Okay, so what we're going to do is we're going to basically change that, and we're going to say these are the algebraic equations, and the neural net here is going to be essentially learned by this part over here. Okay, now that gets replaced over here. This is actually something called index 2. All it says is be careful how you specify the initial conditions, because if you misspecify them, your sequential method fails, but the simultaneous method doesn't. All right, so let's move on. This is how we run this thing, and now what we're going to see is the following thing. 2 layers, neural net. What we're going to find out is fully simultaneous. This thing takes 40 seconds to train with our simultaneous approach. The decomposition, and we used Atom for the training of the neural net on the outer loop, and then we used IPOpt for the inner loop. That took 133 seconds. Not so good. That's for 2 layers, okay? Now let's take a look at what it needs if we need more layers, okay? We went up to 8 layers, 50 neurons per layer, okay? And what you see over here is you see where the time went in IPOpt. And it's basically taking up a lot of time here, and also a lot of time just to evaluate the neural net. That's the simultaneous approach. We get up to 5, and it's already just too expensive. If we wanted to go up to 8, it's not going to get there. At least not if you're impatient. Okay. So what we did was instead take the same two-level decomposition that was slower on 2 layers, but it can handle the 8 layers really well, okay? What's happening is the following. What we're doing is we're saying the time for each atom step pretty much stays the same as we increase the number of trajectories, because we solve the inner problem in parallel. As we increase the number of trajectories, the number of atom steps with time also doesn't increase, okay? It basically stays, it basically saturates after the number of layers here. So this is good. And then finally, as we increase the number of hidden layers, the time per atom step, that's pretty constant. And the time per the number of atom steps, that saturates as well. So as you increase the amount of data that you have, and you basically increase the number of layers, this scales much, much better than the simultaneous method. So you're basically taking advantage of the problem structure and the size and the flexibility in formulating your optimization problem. So you can have a lot of freedom in the decomposition strategy. You have very good tools, and if you have an optimization framework that gives you the freedom to be flexible, you can handle these large problems as well. Okay, so thanks a lot for your attention. A couple things to say in conclusion. First of all, training these neural nets, going from pins to pens, this is something that you can do for neural DAEs. And you can directly enforce physics in the neural net. And the sequential approaches, well, they're still being actively developed, but they have limitations on speed and structure and really can't handle DAs all that well. Simultaneous approach can. And for that reason, we can get faster convergence, and we have flexibility to handle broader scope for decomposition. And that's basically some of the work we're doing now. Okay, so basically, we're doing things that allow us to do things in parallel, for example, with GPUs for nonlinear optimization. There's a group at Los Alamos, actually with some of my former students, that are actually handling much larger optimization problems with decomposition strategies like this, many more than just 1 million variables. Okay, so this in case goes up to 100 million. Okay, and finally, future work. Okay, what we find out is that we want to work on faster decomposition algorithms and parallelization, and we want to adapt digital twins to the structure. There's some theoretical aspects for higher index systems for neural DAEs. We already know how to handle index 2, but we want to go beyond that. We want to deal with noisy data. We haven't come up with any convergence strategies for noise, although we have noise and it works under noise. But we want to know if it converges to the truth system. And finally, we want to extend the trust region filter to pens so that we can guarantee TM convergence. And maybe the one takeaway I wanted to give you for this problem is the following. What we need when we use digital twins for any kind of optimization purpose is we need ground truth validation, okay? Now, if you have a truth model, use it, and you have a trust region filter method that allows you to do that. If you don't have a truth model, then there's an open question here. Can we extend our TRF method to guarantee truth model convergence if we formulate it with pens? That's what we're working on. And I think the answer is yes. You need to validate ground truth with recourse to more data as you solve the optimization problem. Every cycle, we have to go back, correct the digital twin, and solve it again. Once it converges, you know you're at the ground truth optimum. Okay, let me stop here. Thank you very much for your attention. Thanks very much for your interest. Love to take any questions.
Okay, questions?
Lorenz, thank you for the wonderful presentation. I have 2 brief questions. One is about the surrogate, another is about the pen. So about surrogate model, what PSC people did, for example, Marinati, I'm also doing that. So we, for example, for process optimization with a complex reactor module, and we tend to train a Gaussian offline with 30 data points, and then
Yes.
pass that Gaussian to IPL to solve the problem. And when the IPL give us a solution, and we check if the solution is feasible. If it's not feasible, then we add that data point to Gaussian and retrieve the Gaussian, then pass it to the model again. So how does this first truth region filter method compare to this traditional methodology? And one thing I was a little bit sleepy when you talk about that part. Probably you seem like the truth region method, you iterate with the truth model or somehow, and then you also have KKT to guarantee the optimality.
Yeah, okay, good question. What you're proposing to do, where if it's feasible, then what happens is you stop, and if it's infeasible, you take that point and add it to the problem and do it again, right?
Yes.
That's halfway there. Okay, halfway there, okay, compared to what we're doing with TRF, okay? And I'll tell you why. What you are doing when you check if it's feasible and you stop is you're stopping at a feasible point and at a KKT point of the surrogate model, okay? What you're not doing is validating the optimum of the ground truth model, the KKT of the ground truth model, okay? You have to be able to do that, okay? Now, how do you do that? Okay, this is where the trust region comes in, okay? If you have an update of the surrogate model using what we call a zero and a first order correction, then you're making sure that at the base point, your surrogate and your truth model match, and the gradient of the truth model and the surrogate match, okay? So as you converge, the gradients match, and that means
optimality condition. Somehow.
Yes.
Okay.
Then you satisfy the optimality condition of the truth model. Okay.
Oh, okay.
That's the importance. Now, suppose I don't get gradients from my truth model. All right. Suppose I only can get a zero order bias update. Okay. Then the theory says, let the trust region go to zero upon convergence. Okay. That is a very important thing. That was the difference in those two flowcharts I showed with the extra steps. If you let the trust region go to zero, you have to enforce that, and you basically converge because it's going to zero, then the truth model and the surrogate will match, and because of this assumption we make on the surrogate, it has to be a smooth input, well, the truth model has to be a smooth input-output map. It also means that with a zero trust region, the gradients match too. And that's how you make sure you are at the truth model optimum.
Okay, exactly.
But you know, what you're doing is not wrong in terms of making sure of validating it.
Yes.
But if you want the optimum of the truth model, you have to do the extra mile.
Yeah. One quick question regarding the pen you're talking about here. So for the pen, you basically for vanilla neural net, you basically minimize the error, and it's an unconstrained optimization problem. It looks like this physical informed, you are kind of enforce that tuning parameter into the constraint side. I didn't figure out how did you correlate that weighting factor with the ODE with the physical model. I didn't figure it out.
Okay, let me go back there. That's a good question. Yeah. Okay, so over here, you mean this thing here?
Yeah,
okay.
Exactly, yeah.
So there's a weighting factor lambda. I guess it's the one over here, right? Is that the one?
No, I think for
you're going back.
Last row of constraint is the theta actually.
Oh, okay. Well, wait a second. So here, we're going back over here.
Yeah, probably. Yeah.
This one.
This slide.
Yeah. Yeah, that is something that happens whenever you're doing training. It's a regularization term to make sure that you're not overfitting.
Okay.
Okay. So that's your choice. Okay. And there's a parameter that I showed that multiplies that. That's also your choice. So that's basically as you're, and this of course is the data loss over here. And you're minimizing the data loss, but if you're overfitting, this has to be there in order for you to converge to a regular problem. with second order conditions.
Yeah. So we are talking about bilevel. What
Yes.
Bilevel.
Yeah, here's your bilevel problem, right. Okay, so the outer problem, well, let's go back. This is a good question. Go back over here. This is your problem. Okay, objective function is over here. Now, we're minimizing with respect to all these variables over here, okay, including theta. And what you're doing is saying, suppose I fixed theta, okay, then what I would do is basically minimize this, leave this out. All the blue is left out, okay? And that basically just gives me optimality conditions that I can solve. Okay, now on the outer problem, I take what is part of theta, this part, and these variables are dependent on theta, and so that's what I end up with over here, okay? That's the outer part. And then the inner part is basically that problem, which is solved with these KKT conditions. Now, in order to get the gradient that I need to update this part, okay, and I'm using atom here, so this is the gradient that's sent to atom, I get the sensitivity information from these KKT conditions using JAX. This is with respect to theta, okay? So that gives me this guy over here.
Yeah, I think I catch that brief idea. Thank you so much.
Yeah.
Thank you for the wonderful talk again. Yeah.
Thank you.
Hello, Professor. Thank you very much for your nice presentation and learned something new from your presentation. Actually, my question is about the noisy data, missing and incomplete data. That's in practical industry, there's a very big trouble.
Yes.
So in that case, how you can see the digital twins that integrate with this, the regional truth regional filter that improve the surrogate integrity and the robustness of the optimization? Thank you very much.
Yes. Okay, thank you for the question. I don't have a full answer yet. I think there's a lot of research that needs to be done. I do think that these things help. Okay, if you have a truth model, okay, that you can train your data on, then that will make a difference even if it's noisy. Okay, you can be clever about how you formulate the optimization problem with noise, okay? And one of the things that's nice is you still preserve the physics. And so in both the parts of the talk where we had a truth model and we used the trust region filter, if we had some noise and we could basically say this prediction is going to be within these upper and lower bounds, we can come up with some probabilistic objective function, okay, that will deal with that. Similarly, with training the neural net, that we actually have noise anyway. And so for that, what we have is something like this. Let me go back here. Yeah, we have a problem here where we're minimizing this deviation that's basically due to the noise, and we're adding that in the objective function. Okay, so this is not the answer, but it is a good way to deal with it, okay? Now, the question is, if that noise is actually meaning that the physics are wrong, or at least, can't be characterized, then we don't know what characterizes the optimum of the truth model either. And so there are ways that people have looked at stochastic optimization problems. I'm not that familiar, but I'd like to know more about how to do that myself. And so that's just essentially where things stand.
Thank you. Thank you very much, Professor, for the answer.
Thank you.
Thank you.
Thank you, Professor, for your very inspiring talk. We are in our lab. We are doing something about active learning. So that is actually very similar to digital twins. We need to train a surrogate model. And my question is about when you are using PIN or PNN with the training of surrogate model, can you actually do the hyperparameter tuning at the same time?
Yeah, you can. Not directly within the algorithm, but with a strategy that uses that algorithm. Okay, and for example, this thing here, if you look over here, the decomposition that I showed here, what we're going to do is we're going to take a look at this part over here. This, if I want, let's say that I have some hyperparameters. Let's call that mu, maybe one of the hyperparameters, okay? And I have this solution here, okay? And I want to train that solution with the hyperparameters. And now the position that I have with theta, I can include hyperparameters, get the gradients here, and then the outer problem also can be used for tuning the hyperparameters. The inner problems basically, so what I'm trying to say, it's a bit confusing maybe, I've got two levels here, okay? Now, my hyperparameters could be a third level, or if I'm clever, I could maybe combine it with the outer level, but I can put in another level as a solution strategy, get sensitivities from the inner levels, and use that to update the hyperparameters for tuning. Okay, so that's something to think about if you want to do that in kind of a more formal solution strategy.
Thank you very much.
Sure.
Other questions? No, let's thank Professor BIEGLER again for this wonderful talk.
Thank you.